Okay, so to look at it today, one of the few things that jumped out from the beginning was that we have some overlap between some of the sensor schematics. For example, if you look at C3, we have two of them. One of that refers to the actual sensors, and one that refers to the BMS chip. You want to make sure that every component has a unique identifier, because that's what you'll use to map it in the actual PCB, and it'll help you route it more easily if you don't have two contradicting designators. So that's one thing I would do. You can do basically, like, imagine if this is like, if you see here, there's a square bracket on the left side. You have two sensor connections, one for pin mapping. You could put like one in front of all the number like items. So this would be R12, right? But then you'll see, like, that might just look as 12, right? But then you'll have to find a naming scheme where just make sure that when you start on the first page, these ones are all numbered, and then the ones on the second page and whatnot all follow off that numbering to make sure that everything has a unique identifier. And that makes it a lot easier to manage. And then once you have all those unique identifiers going for you, then what you can do now is then go to the PCB. Right now, because I searched up a component, for example, C33, it'll put you in the PCB filter. What you can do is go into the panels, go into PCB filter, and you can clear the filter, and that will allow you to basically touch other components again. Just because when you have the filter on, it only lets you touch the component that you search for. So today we'll do some routing for the MCU, for the memory chip, and for the power electronics chips, just kind of give you an idea of how to do it. So one of the first things I would do when you're routing, you just get rid of anything that's not essential. So things that could be essential is basically these batteries, where they're at, that can be essential depending on how the enclosure was designed. Then the mounting holes, that would be enclosure specific too. So I would set an origin. So by doing that, you see how here at the bottom left corner is the origin. We can use that. Then you want to keep track of what the X and Y coordinate position is for the holes here. So you're able to keep track of that, because those probably align with some type of 3D design or hole on the enclosure. Right. So one of the first things I would do when you do a PCB layout is basically, like, here you see a lot of mess. What you can do is that you can always just delete everything, just to kind of give you a clearer view, right? And what you can do is that all those components that you delete, you could just regenerate, and then they'll go somewhere over here to the right side, right? But now your working area is clean, right? We can also delete this, and also, as well as you see now, there's less mess and less of the spider webs hovering around in this area, which makes it a lot easier. Another thing too that's missing from a traditional board layout is that there's no board outline, and one of the easiest ways to do that is just to draw a board outline on mechanical layer 1. Mechanical layer 1 is kind of like an industry standard of what is considered a board outline, but one of the things too, you have to make sure that you're actually able to, let me make this 0.001, it rounds down to 0, but make sure you're able to have finer lines. But right now what I'm trying to do is basically just find a way to snap onto the grid without it giving me so much problems. Because if you see there, when I was trying to draw it, here, now I have this here. No, I think I must have lost that. We can make the line a little bit thicker for now, like 1 millimeter maybe, 0.5 millimeter. Alright, just so it's more easier to visibly see. I'll make it smaller for now. Okay, here we go. We can see it now easily. And now I'm just doing shift space to kind of follow the contour, like the outline of this. And you see here, I'm having a problem snapping to the edge of the board. So and if you see here, like the board traditionally isn't on a grid line at all, which is pretty problematic, right? What do you see here? Yeah. I don't know, it's just basically using the grid here. Yeah. And one of the important things too about a PCB and using a grid is that it lines up to whatever you're basically CADing in a sense. So at this point, I would honestly just make the PCB layout to an actual like dimension that makes sense, because right now it's not swapping, it's like not snapping correctly to anything, which is not great. And one of the biggest things about like in mechanical design is, see, one thing you have to look about here is that you want to choose like the outer curve, right? Which is ideal. Like for this design, it's not bad because this won't see a lot of vibrations or any of the sort. But if this was actually mounted, for example, a car or something, then these mounting holes would basically tear right off the PCB, just because they just have no like material to actually like click into. And one of the things I don't want to do is basically move these. Yeah, I can move it up a little bit, right? Because if I move these, then what can happen, right, is that, for example, here I can do pass centers via centers to board outline. You can kind of see how far this goes to here, and that's why it's 0.409. And you see here, like it's just, this is off to, so there's more from here. So basically I will just kind of pull this back, right? And then I'll change the grid by pressing G again. And I'm just kind of trying to match it a little bit. You can't really do too well, but honestly, that's fine. This is just going to be stationary in a greenhouse, so it's not like vibrations are going to be important. But what a board layout allows us to do pretty much, and now I can snap this to the board layout. Here, let me grab onto here, right, and then I'll snap this, like basically board cutout area away from there. So I don't really need a board cutout anymore for this, but what you can do now is you do Shift S to only see the mechanical layer 1. Right, and I believe this is relatively straight, but what we could do now is design, and then we could do board shape, and then we can do define board shape from selected objects, and that basically cuts down the shape. Now we have our board shape. So one thing we can do now is go into the 1 key, right? And I basically, here we can design, I believe we can edit board shape. So now that we have the mechanical layer 1 down, we can always basically build our board back by doing like the highlighting, you know, do Shift S so you only see the mechanical layer that we set up. You can highlight it, design, board shape, and then define shape from selected objects, and that will basically set it for you. But what I did here was I kind of just extended the grid, and this kind of gives us like a play area, right? So one thing you want to do is make sure, so this pink line here would be the like the theoretical board edge that we're going to have. So basically I want this antenna relatively close to what that is, and then we can make sure that like dimension wise it's not terrible, right? And then what you can do too is that we can kind of see where these line up. Okay, and then that'll be 93 divided by 2. That's 46.5 millimeters. Okay. That'll be 46.5. So we'll put that right in the middle. Right? And then now you want to look at things that are important. Okay, give me 1 second. I'm just going to pause this. Okay, so we're back. So one of the things you want to do is just kind of see how the pins are. If you see here, there's no real way to kind of line this up. Right? You see that this pin is very accessible. The next pin would be this one, right? So then one thing you might do is then put this on the other side and see how accessible that is now, right? And you might be able to be like, oh, this might be a lot more accessible and easier to connect to. One thing too, I don't believe we're using this pin for anything, but that's really depends on, if you see there's nothing really connected here, so we can kind of just like bypass things here directly, right? But what we can do is, because this has to connect here, right? One thing that we can do too is that for traces, it's usually better to use something that is a little bit bigger. You can kind of get away from like 6 mil to 8 mil for everything. Right. We want that to actually be 6 mil, so if it allows us. Okay. So now I press Control W, and then next thing here. So I'll have this here. Right. And even though there's a small difference between this length and this length, because they're relatively so small, it really shouldn't matter too much. One thing I always recommend too is when you put down components, for example, if you press Q, Q is a good button because you're able to switch between the two dimensions, but it's good to kind of, I say always put like your PCB kind of to like 1 millimeter when you're placing components, so you can kind of think about the space that your soldering iron would need, right? And then you can move it together later, but just make sure it doesn't stick too close to each other. Like 0.5 is fine. We have to consider, like, if you have an MCU, for example, here, can you put your soldering iron between these two, or like with the solder bridge between these two? It's like probably not. So we could just keep connecting these up, and you see there, like, it's all good. Okay, yeah, that's just going to be approximated, so it's fine. So that's done with the crystal. Another thing that we want to care about too is pretty much this guy here, just because it's one of the more important signals that we have. But one of the big things about this is that it's like a bigger, a lot of signals here are very important. So one thing you want to consider is that we'll get ground later. Ground isn't very important for us to route unless it's like a power electronics one, that we can put some dedicated ground plane around there as dictated by the data sheet, but we can just consider we'll get ground later. Same thing with power, you can kind of get away with it. So one thing you want to do for inductors are here, this is really big. So what you can do is you can find similar, you can find designators, same. You can say top overlay, this back and top overlay, so we'll leave it the same. We also have this text the same, right? And then we can just apply and see what it finds. But basically, what we have here is the text that we have, right? And what this is basically like, we choose a text, and what we can do is basically look up just the PCB text capabilities, and it might give it to us, or we just have to look for it. And this is legend, so the text height is 1 millimeter. So I'm just gonna leave it at that. Even this thing should be bigger because this won't print out properly. What we can do is here, press OK. I'll put here, 1.0 millimeter. Oh, there you go. This must be set up as a different type of font, maybe. Here, true type. We can give it like a font. There you go. And I can make it bold now. And then this text is still relatively small. Right. This will probably hold up. But now these are all kind of like similar sizes. Right. And then we can actually make sure this is like a proper height. Ish. Okay, it's a little bit shorter than what we probably need, but we can just basically move that up a little bit more. Alright, let's see if that's 1 millimeter, and that helps us basically get these designator out of the way when we route. Just so they're not awful, and if it's like a very like obvious landmarker, for example, this pad, you know it's the crystal. You don't need to have the Y1 here. You can hide that, and that makes it so it doesn't appear anymore. And the PCB that you print out won't have it either. Right? So there's some things, like for example, big ICs like this. You'll know that this is U15. It's like one of the few chips that look like this. So this one you don't really need it either. So basically what I do is that you find here, and you just press space until you find the pattern where the spider webs, quote unquote, kind of look the least complicated. And this is kind of like a pull-up resistor. This isn't really essential, so we can kind of let this kind of go anywhere for now. Like, this isn't that big of an importance for us. This is a decoupling capacitor, and one of the biggest things about this is that the closer you have it to, so when you look at any type of impedance, right, usually you can see like there's a kind of like this, where you have kind of like this drop that comes down here, or like this one would be a good example, where you have this drop that goes down here, right, and then back up. And if you find like what contributes to the impedance of a capacitor, what contributes to the impedance of an inductor, you'll find out which side is the inductive side, which side is the capacitive side, depending on the frequency. Alright, so one of the best things you can do for the inductive side of the capacitor is by minimizing the loop inductance, and that's by keeping this relatively close, and that's why usually people pick smaller capacitors. Right, so what you want to do here is then to basically try to minimize the distance between this and that but you want to make sure it's not too close to the point where the silk screen disappears, or the solder mask, which is the green stuff, because then it can scratch away and then cause these two to bridge. Right, so this is relatively good. We can make it so the purples touch each other, but you have to think to yourself, what are the problems that having these two things too close together would cause you when you're soldering, right? And now you see here, this is one of the outer right ones, so you can keep like 45 degrees bends for now, but what I usually do is I go to a smaller dimension plane whenever you do any type of trace or routing, right? Or if you want it to be very structured, you can choose like a higher plane. A lot of like really tight and high frequency designs usually relatively look like someone has hand drawn the traces. But what you want to do is kind of do your best to give this space, right? And then if you see here, right, let's see where does this signal look on. You can press Control, you can kind of see where it's coming from. So if you see this one here, I probably shouldn't have that come over there if this wants to go up here instead. And then you see here that wasn't fitting nicely, so this is one of the perks of having this. And then you can kind of evenly space them apart. It doesn't have to be perfect. This one, it doesn't matter if it goes in like this, right? I'm just basically making sure things are kind of well spaced away from each other as much as it can. And you just want to like minimize bends, but also things like sharp angles, like for example, bridging like this would be a bad idea because this sharp angle can capture acid, and that acid can cause manufacturing problems. So if you're ever to branch off a trace, you want to do it like this, where you have 90 degrees angles that allows the acid to flow out, but that's not as much of a problem anymore with modern manufacturing. Now we have to look at this side. So you see here, one thing that this happens is this crosses over here. This also wants to come around out here. And this is kind of where you might run into headaches when you're routing, because if you see here, now I'm kind of completely cut off. So then now you wonder to yourself, like, what could be done to resolve this, right? And then sometimes that just requires you trying a different outline, because what you would have to do here is pretty much just use a via. Right. Right, and then from this via, you're then able to, make another connection here, right? And then that will allow you to connect to this, right? Which isn't always the most ideal, because this is our first thing that we are laying down with the highest signals. So we don't want to, we want to give it the best shot it can without giving it, you know, without compromising on the signal integrity. So then you might take another look at it and see how things are kind of wired around, right? Because before I had CS down here, right? So maybe you might look at it like this, for example, or maybe you might even take a look like this, right? You want to kind of play around with things like that. And for chips like this, you can't really go wrong, per se. Like, for example, here, right? And then here, we can do that. And then what we can do here is then, yeah. So a lot of PCBing is just playing around until you find a better outline. And if you hold control, it gives you more like freedom. And you see now, like, this is one thing, right? And then we can just put this here for now because we know that will be connected, right? Oh, we connected over on this side. This is the resistor, right? And then this guy will be here, and nothing is really blocking it right now. So now we want to look at these signals. So one thing like I've done was move this over a little bit to the left so things don't kind of have to squeeze through this area here. But then basically you see here now, like this will hit this. Right, and this might look a little ugly, but we can make it a little bit nicer, right? And now this will have to come. So one thing I could have done was move this down a little bit so this doesn't have to be so aggressively squashed, right? But then you see here, this now goes down here, it goes here, and now we only have, if you look at this now, if I was to clean this up and all these up, so imagine I clean this up, right? I clean this up. And it's okay. We can make this look nice and give it ample space, right? What we're trying to do now is just find a good way to connect this without having so much. And here what I'm trying to do is just make it even between here, because if this is gonna, yeah, just give it the best chance of being manufactured, because the more space you have there when they actually drill out the copper in this sheet, then having it too close like this might give the drill problems. So giving it the most space possible through that gap is the best way to make sure that your device is going to be manufacturable, right? And then what we can do now is select this little piece here, and that's fine. And now we can kind of, you can kind of count the diagonal dots away, right? And you can kind of like see here, we can kind of make this not taper so aggressively, but sometimes it might just fight you. And then the only way to kind of deal with that is by just deleting that here and deleting that. And then you can just do it more gradual. And you can go on a lower one, right? And you kind of just have to like wiggle around and play with it, right? And now that's good. So I'll go back to the higher grid, right? And now that I move this down, you'll see that, oh shoot, you'll see that we have a lot more space now to wiggle around. So what we can do now is just kind of like, you can go here too. If you see these are both obtuse angles, relatively fine. Same with here too, but we can give it a little bit more space. We can get rid of this kink here, And then we can kind of back off on this. We draw these lines here. And now you see like the one line that we have is this one here. And there is ways to kind of get around it, right? For example, if I came out this way, right, that gives space for this one, right, to also come through, you know, here, but then you hit here, right? So then this will be one way, but then you see this is like basically crowding near a bunch of things, right? But then you also see here too that these lines are all being used. So this probably is going to eventually be a line that comes out. This will probably be a line that comes out. This will probably be a line, right? So you kind of have to pick and choose your battles, and you might have to come back to this. But like the best thing about PCBing, or like the most important thing you can do, is kind of start Bob Rossing it, right? And like you see here, that like resulted in a lot of extra bends when I could just easily just tie it here or here, right? And this is good enough. There's no sharp angle. There's a little bit of that, but you can always just like put it in like this, and that's relatively fine. And then, right, and then we can do this, but now we still want some space for the, so what we can do now is that we can put a via wherever that via is that I had last time. So yeah, just make sure when you do a via size, it's actually manufactured by JLC PCB, so you just want to go to their website and check. And then always do tented, which means go to manual and then take the via, and that basically means that things won't go through it. Here, let's look up the via size drilling. And then you see here we have via, which is diameter minimum, but you have to be careful with these type of things because you'll pay a lot more money for the smaller via sizes. So this is 0.45. So just so I don't do the minimum, I might be doing 0.25. And then, yeah, something like that. Yeah. 0.25, but I think you can also get away with 0.3. And then I'll make this 0.5, maybe. And then you can also tell if it's good because you can do design rules and see if that's the proper size. But imagine you had a bunch of these and you want to kind of resize them. It's relatively easy because you can do that right click, find similar objects, and you can select all the vias that you need. Right, but one thing that you can do now, right, so I have this guy that I copy, and I kind of just copy and paste vias from places, right? These vias might be a little bit big, but the one thing that helps you a lot is if your via is smaller, you get a better capacitance, but then I'll put that back to 4.5, because I think you just need to be 0.15, or it might be greater than 0.15 more, so it might give us an error if I don't have more than that, but it's fine. It's not going to basically change too much of what we're going to be doing, but basically what we want to do now is just find a place where this is kind of like even in the middle here, right? And what we want to do is kind of just like, right here, let me get rid of it actually. So that's kind of like the idea, is that we'll just put it like this to here. We can put this here. We can kind of like match it, right? And then because we'll need space for the via, right? What we're going to need to do is then kind of meet it out here. So we'll have to have some type of via out here, right? And that looks good to me. You see here, really obtuse angles, obtuse angle. Right, and I'm not going crazy. Usually, if you can, you'd make all the bends relatively like. You want to always like make things as straight as possible, because every bend is like a change in impedance, and that means like additional ringing, additional noise. But like, you have the physical limitations where you do need to have bends in this, or else it's not gonna. You're never gonna be able to route it. So, yeah, you have to pick and choose your battle. So, here you go. And what you can do is kind of, because you're on the bottom plane, right, you can kind of just go here and just take that, right? One thing that's kind of bad where I did here, but it might be just an exception for this IC, is that we have traces that are moving more vertical on the board, and this blue side on the other side is also moving vertical. Usually you want to do like more of a hatching pattern where you do like the bottom layer is horizontal, the top layer is vertical, or vice versa. Right, you want kind of there to be a flow. And as you plan out like the other connectors in that, you kind of get an idea, right? So now we'll do the remaining components, right? And this resistor can get moved around. It doesn't matter if it's like this, like this. We're going to assume you have a ground, right? And if you want to make sure you have a ground, you can just copy a via to it here. And then when we add a via to the mid layer and the third mid layer, and then we like stitch the two planes together to form all the ground planes across all of them, then it's gonna figure itself out. And then we're also gonna be doing power last as well. Because one thing about like power, right, is that you have the ability to kind of route it all over the board. So for example, see this 3v3 pull up? You can basically, you see how it kind of goes big? You can just choose a very big trace, and with bigger traces, for example, like 101 millimeter trace, right? This will have very small drop. So like if you really needed to, you can make this thing go around the board like this. Right, and because it's flat DC, it won't really cause noise for other lines around it because the filtering is supposed to be good. So you can kind of go crazy with DC. It's these DC lines or digital lines that have transients, or even the analog stuff too that also have transients, because you have changing voltages, changing currents that are going to cause problems for your other signals. That's why for power, imagine you had a bunch of stuff like right here. For example, imagine this guy was like right here. It's okay for you to kind of route power like this, because it won't be that much of a difference here, right? It wouldn't matter as much. But because we have the leniency, what I would usually do is do this last or later, but you'll probably have some connection like this, right? That's basically connecting these two. But I would always hold off on any type of like power related routing until later, unless it's specific to like power electronics, because then that would actually have some precedence because of the switching. Let me put that back to where you had it. So the next thing that we were going to take a look at today, right, is this TPS, and I think I might have moved it into this larger group of components here. Okay. So let me go and take a look. the converters to make sure we have everything 56, 19, 18, 03, and then 21. 21 here. So I kind of gave us a lot of, you can always leave this via. I usually just copy the via in place. Just find a workflow that's like good for you. I'll usually come back here to get the via. But yeah, for example, this might flag, the pad here might flag the design rules because the vias here are really small. So one thing you have to might do later on in a change is go into here and then change the vias used here to be a little bit bigger. So then it actually works with the rest of the board. But one thing we can do here now, so I always recommend going to the data sheet and kind of understanding what it talks to. One thing too about inductors, they're very noisy. So usually what you want to do is you can route the board, like route this, and then orient it. So imagine you did all the routing, right? And then you have all these things connected to each other, blah, 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 blah. Right? You can just highlight this whole thing and kind of rotate it until the inductor is kind of like on the edge of the board. And that's why if you ever look at these type of layouts, they usually make the inductor very easy. They put it to one side, so it's kind of easy. And what that does is, like, imagine if you have like an analog circuit. For example, one of these are an ADC, but yeah, I won't go ahead and just mess it up on you. But imagine if, yeah, this is an ADC. So like this being right next to this, like this would inject a lot of noise into the ADC. So you just, yeah, you don't want to do that. Let me just go back and put that back. It's always recommended to kind of keep a lot of the high current or more noisier current items and voltage items away from any analog signals and whatnot. And a good idea to do that is just keep this away, the inductor away, close to a board edge. And you'll see a lot of designs that tend to do that where there's sensitive electronics in place. But we can just figure it out as we go. So one thing you want to think about when you do a lot of power electronics design and layout is what is the intended purpose. So here you kind of see we have a connection here, which is S switch and TLEN. But then for some reason, we don't have pin 2 on this. So let's go and see why we don't have pin 2 here. So we have this here, right? Yeah, this is just pin 1. There should be another pin 2 here. So what you'd want to do, ideally, is this is U12. I want to find out where this is. Okay. Yeah, you might want to save this component and edit it, because what you want to do is basically have that pin be pin 2. You want the second pin there. Right, and that's I'm pretty sure if you come up here to the actual pinout, right, if it's somewhere, you'll have a type of pin 2, right, because even here it has 2 switches connections here on the actual IC. But it might be because the body is different, but because here it would be hard to do this layout because you have a very different chip layout. Okay, where's the pinout? Okay, so we see here the RSA pin 2. Oh no, here, I think, which one are we? Is this RSA? Let me just take this. And let's look at DigiKey. I'm guessing this is the RSA one. So, yeah, that's something that you'll have to confirm tomorrow. But assuming that this is the RSA one, okay. See what here we have. So this one is the PWP package, which is this pin out here, right? Yeah, I need to review these better. I took a review of them originally, but I'm still in progress with the BMS. So this is something that has to be done. So basically what we have to do is that pin 2 should be connected to switch here, right? And also, this is the one thing I like about PCB routing, where it's also a very good place where you can kind of figure out and troubleshoot the board. Because I only caught this because by my intuition, it doesn't make sense for the designer to leave this pin disconnected. Because what you want to do, right? I'm going to just make this temporarily TPSW just so it works. But make sure you update this in the actual model. Right? And just make sure the rest of these pins are actually correct. Because, yeah, it looks like it's alright for now. So this doesn't have a big idea for us. So one thing we can do is that you see here, this kind of gives us like a harder time. Because our TN, EN, okay, so that's TN, EN. And that goes directly off the inductor, right? Let me just go back and confirm. Okay. And you see here, TN, EN is basically just the input, basically where we're getting the voltage. So this is just basically like whenever the voltage is coming in, right, would be kind of the same. So this will be connected kind of to this, right? This will also be kind of, so this can be connected like this, right? So this is just an enable pin, so that's not as important. But basically, you see here, this is kind of all ground. So one thing that, because for an inductor, right, things are kind of going there, and then we want to kind of look into what the input will be. So we also have C21 that's going to be on this side too in the input. So I'll bring that along. Right, but basically we're going to have something like this. So you can still use the data sheet as an example, right, of how things should be laid out, even though it's different. But when you take a look at the data sheet, a lot of the things you see here, right, is like the switch here is relatively large. They usually use multiple pins to have a bigger area, because by having a larger like area of copper, you're basically reducing the loop inductance by increasing the capacitance in this area, and that helps like gigantic voltage spikes that happen from the drop of inductance. So that's why usually whenever you see any type of like switching, like for example, if you're controlling the gate of a MOSFET, because the signal is always on and off, ideally you want the connection to that to be really big and ideally very short. And that's why if you see here, this is like a very short and stubby, but very like big area here. So one thing you don't want to do is do this, right? And just have a small trace. What you kind of want to do is build up to it. So what you can do is what you can kind of see what they want to do is they want to build up to the surface area. So what you want to do, and I would recommend just using like decent plane, is just you want to kind of just build up something and just taper to it in a sense. So here you can kind of go like this and this, and then you can kind of like follow the pad here. It's a little bit weird because I made a mistake up with this one here. So let me just do that again. Right, but basically, polygon pour. Right, and we can taper. We can move that back later, but basically what we're doing here, right? So what we're going to do here, right, is basically, we can fix this a little bit, but what I'm doing here, right, is kind of similar to what they were doing in the data sheet. And one thing I always do is pour over all set name objects, right, and then pour. And then what I usually do also is turn off the heat, what you call thermal reliefs, because you really don't need them, right? But let me kind of do that as an example. So we go polygon point, polygon manager, then we find the TPSW, and we do new connect style. We go direct connect, and direct connect, and then okay. And then we'll re-pour. So what this does is that we're kind of trying to keep this as thick as we can the entire way of its routing. And what that does is essentially keep the trace width wide, increasing capacitance, and making sure that the trace isn't thin, right? Which is basically, we're helping basically add more of a capacitive effect to this inductive path because of this inductor, helping provide more stability compared to because when there's a change in current, this inductor is going to drop a voltage, right? And the more capacitance or charge we're able to hold here will help out with that to eliminate any like high frequency ringing. So that's kind of like the whole idea between like the switching components and that. And then here, what you can do here is just basically like, for example, this one's relatively small because you might have a lot of power coming in, right? Like the only way to know how much copper to actually put is by doing thermal calculations or thermal simulations. But when you're just making a PCB, you just kind of need to do what feels right, because unless you spend the time to do thermal calculations, you're not going to have a good guess, and you do not have the time to do thermal calculations. And that's why people would usually design stuff first, right? And if they find out they have a thermal problem, then they'll go and spend the time then to figure out this thermal problem that they have, right? And then same thing, I'm not going to remove the polygon or like the reliefs, but I would recommend removing the thermal reliefs. But then you kind of see this. So this is kind of how we set this up. So this is kind of the input. And what you can do is just like, imagine this was like coming from somewhere, right? So now you can kind of like imagine you have this coming from the batteries, right? From here, you can have it like boom, and then connect here. And then because this isn't the same net, it's fighting it, but that's kind of the whole premise behind that. You give it like a good surface area to connect, right? So another thing you see here too is that if you see here, the inductors on the top right, a lot of the analog sensing, for example, the feedback is at the bottom of it. So the whole idea behind that, like I told you, how we keep the inductor towards the edge of the board, right? So for example, I take everything here, right? And then this, right? Oh yeah, and we also need to, what you can do from here, right, is that you can put like, you can take from like the capacitor side. Here, let me put this 6 mil, but you also want to see why this is taking in this voltage too, right? But in reality, it's like you can only have traces as thick as the pins. So if you have the space, I would just recommend having a trace that's, you know, as thick as the traces. So maybe 12 mil. 12 mils and beginning, so 14 mil, right? But the input should be, it's not 100% stable, but it isn't as noisy as the actual inductor itself. But then, for example, you can do something like this where it connects to this, right? And that'll probably be well okay. But then you see here, ground kind of gets cut off, but it also has a ground here. So any type of port that you put down will just connect these automatically. And one thing that you can do too is that you can get some of these vias that I have here, right? So if you move this down here maybe a little bit, or here, or maybe if I move this away a little bit away if I can, right, to give that more space, right? Now what we can do is that we can now polygon pour, right? And we can kind of just like, here, let me put this here, but we can kind of, I'd always recommend using the grid because it's easier, but basically we have now, so and you also want to respect the things around it because newer polygons, I believe, take precedence, but right now we can do is just basically give this a ground signal here. We can re-pour for overall same net objects. Okay, this kind of is looking bad, so let me just go to the polygon pores and just select everything and do a new connect style and just make it all direct connect. Right, and then we report this, right? But one thing you can do is kind of just like connect this here. And that's kind of like the whole idea behind that. Because like you see here, there's somewhere like the P ground kind of just like hovers on itself. Right? And there's no way, like you see here, this can't go really anywhere. It says it goes under the inductor, but like you don't really get that much space to go under the inductor, right? And you can kind of try cutting back on these pads, right? Which you can do a little bit, right? But like this is just gonna like doing this, right? You can put ground here, right? But this will be relatively good enough, right? They just want to power ground, and then like there was a study from Creed that talks about power density in diodes, and it's basically if you have a bunch of little diodes around like an area like this, kind of like similar to an LED, like I believe it was like 6 to 10, and you'll like cap out in any improvement. So if you see here, this one puts a 2 here, 2 there, so like we don't have to go as crazy dense, but you can just spread them out nicely, right? Like I said, you're not really gonna, this is more like a stitch, because you know there's gonna be ground underneath, and it's gonna connect automatically to this middle area here, right? And then this is ground, so you're gonna assume that this is gonna find ground somehow. But what you can always do too is that you can just kind of put this here, and that ensures that even if you forget to route ground, right, it's still gonna have a path to ground, right? And then, yeah, these things will also have a path to ground too. So if you really want to, what you can also do is just another polygon pour and just dedicate this area. And you can kind of make it even around there, but I'm just trying to do this quick and dirty now. But basically, right, you can have this here, right? You can have that there, right? Yeah, this doesn't really tell you which one's the analog ground. Let's see. That will change the whole game plan, because I just noticed the other side of the chip doesn't really have, well, this is all P ground. Huh. Okay, so this will be the analog ground 12. Okay. And 7 and 8 are just like, are not ground, those are just also connections. So it's like, yeah, you didn't have to do all this either. There's real no point to it other than like, you know, just making it look nice and conform, right? But in the end of the day, because these are just like 2 connections for LBI and sync, you could have just like put a via or a line from here to here and a line to here to there for those 2. So it's good to understand what the actual signal is, right? And then make it pour overall same net, right? And that's relatively good. So now we have the ground side. So in our design, we probably want this to kind of, because this is close to the battery, what you probably want to do is probably put it up here, because it's like a lot of the power is going to be coming from the battery, depending on where side we put the BMS chip, right? So, right, we'll probably do it like this, or we'll do it like this, just to keep it away from any of the analog electronics, right? But you know how I'm already like routing it off the board here, right? You can route it anywhere, kind of, and then move it to where you need it, right? And then now we have the analog part, so you can kind of take some inspiration to what they have still. In the end of the day, you just need to do your best, and if anything's really bad, then we can talk about it. But you know, like you see here, LBI and the sink are just connected through a small trace. So there might be like a little bit of decoupling from the ground when you do it through a trace like that that's small. So you might see some like gain from having it like this, but you also notice here that this didn't really connect to each other. So in reality, what it looks like that they had was just like, yeah, whatever the ground is, you kind of just connect it through a small portion, right? And that kind of helps decouple some of the noise from the main ground. It's like if you put like a resistor like this, not a resistor, but this acts kind of like a resistor, and that kind of helps filter it, but then also decreases the potential between these two just because there's a voltage drop. So there's nuances between that, but honestly, just leave it like this. Imagine like getting rid of the thermal relief would be fine, right? And if you really care, then what you can do is also just like have it like this, and then kind of match it, right? But that is relatively like a direct connect from ground. It's actually, yeah, between how they're connected to each other, which is kind of like this, right? So that'd be fine too. And one thing we can do now is just like, what I usually do is just do all the polygons and then do new connect style towards the end, kind of, after selecting them all with Control A. Right, and then report on. Right, and then, yeah, that's good enough, honestly. Then you ask yourself, what is that pin 9 for? So what I look at now is the data sheet, and what is pin 9? Pin 9 is enable. So what we can do is that we can use a via, and I'm going to take it from over here. And it's just an enable, so it's the same thing as like a GPIO. It doesn't, it's always going to be on. It's always going to be constant voltage, just be pretty stable. Because it's like a constant voltage and like pretty stable because it's always on all the time, you can kind of route it around everything. So it can be one of those things you do last, right? But it's one of these things that can like kind of move out of the way, or it can kind of go to another layer and kind of go out of its way to make the connection, because it's like its actual connection isn't that important, right? Or it's like you don't care about the signal and the quality of the signal here. It's not an analog signal. It's kind of just like a DC, always high or always low. For this instance, it's always high, right? And then, yeah, you have this here, right? And now you have these three that are V out. And then we can go back to the data sheet. And then what does V out have? So when we go back to the data sheet, it says see, one of the V outs used for feedback, one of the V outs are kind of, oh yeah, they're all just connected like this. So what you can do, because you have so many of them, is that we find out what capacitor for V out is the one that should be close, which is usually we have capacitor 2, capacitor 1. Oh, and I see here. So you wanted this kind of disconnected from the exposed pad. And this is all P ground, so you want these to be kind of separated from each other, actually. Oh. But ground still has to come from here. So this is fine here. So this will be kind of still part of the analog ground signal, right? It's going to be sometimes more details about what to do with the grounds here, right? And then here it tells you this avoids ground shift problems. To the control ground pin of the IC, the feedback divider. So basically, these might be problematic because they're bigger, but this is the beauty of routing components. While you build them, you kind of see what needs to be reworked and what doesn't. So it says that one of them has to be directly to the pin, so it would be like this kind of. So one of these would be kind of like here for feedback. One of them would be here, right? But then if you look here, this is kind of awkward, right? All right. Yeah, here is like not a lot we can do with that because these are so big. That's okay. And if you see here, this feedback kind of goes out like a T, right? So maybe we can leverage that idea where we have this here. And this can also be leveraged like that too, right? And this can also be leveraged here too. And then this can also be here too. And what that does, making sure the spaces are all good too, by the way. You don't want to put these too close to each other, right? So you can kind of take inspiration with the data sheet said, right? So this would be our P ground, quote unquote, right? And you see here, I'm having a problem snapping to that now. So you can go to the properties. I can turn on the tracks. And then right, and now what we can do is kind of like connect this and that together and kind of wiggle around with it, and that's good enough, honestly. But now we have this, so you know what? You see a bunch of the same net kind of hovering around each other, and you kind of look here on the V out, you have kind of like a big part here, and these kind of like all pull from there. So what you can do is then kind of just polygon pour it, right? Like we've been doing, and you kind of just, right, you want to kind of go a little bit more accurate, right? Wait, and you see that like that doesn't need to go that high. So this will just go from here. I'll cover this. I'll cover this, and then I'll cover this, and then I'll kind of come back around over here. Right, and you can kind of just touch it up after. But Right, this can kind of go higher. This can come down more angled. Right, and it's like, I'm not really using too much brain power here. If you think about it, a lot of this capacitance is just here to kind of give it a good charge, right? Or give a good filtering. And like these have effective capacitance that do some type of like filtering and also give some type of like charge, right? You get unity power from these maybe, right? But for example, imagine if you connected these all through a tiny like trace. Any type of fluctuations or anything like that might be used, like any of the charge here might be used to kind of make up for any of those fluctuations. Right? Compared to if you keep it all on one plane here, like one wide plane, kind of helps with the capacitance, and it provides charges in this area and allows charges to move around a lot. And there's not a lot of inductance between these two because there's like, you have a lot of width for the trace. So it means that this capacitance will be more used for filtering rather than decoupling any inductive paths between them, right? Because the smaller the traces are, one thing you can do too is you can move this up. So you can move this a little bit down away from this pad, but, right? And then I do all the who has, but you can kind of get the idea if this was all filtered in and connected, right? And then that's kind of the whole idea behind this, right? And one thing now is that you have some type of like analog ground. And the analog ground, right, has to be kind of, like one thing you can do too is use like a bigger trace here, right? And then what you want to do now is have these like power ground and analog ground. You see, this is kind of like, you kind of want to take a look at this and be like, where does the power come in? Where does the input come in, right? And what some people do is that because this is analog ground and this is analog ground, they actually separate these two. And they would like kind of make this their own little like square area here. And you want to do it all away from like the inductor here. But what they would do sometimes is that you can have some type of copper pour, like this maybe. You know, and then what you want to do now, if this is ground, or this will be kind of like your theoretical analog ground. So what sometimes people do is that they just connect like a thin trace between here and the power ground here. And that kind of, like what I said before, it helps kind of add like some type of resistance to help remove, but then it also causes like, it can cause potential problems because the potential wouldn't be the same. Yeah, but then you see this too. It's like P ground connects through here, that connects through there. So honestly, yeah, that's just overthinking it. And then this can just like, yeah, you can have that connect up here, but then you do a fill, it'll probably connect itself. I think it more cares that this is connected to here really close to mitigate any noise from the inductor here. Because if you had this trace here kind of wrapping around, like if somehow you're able to get this to kind of go, for example, this would be a really bad idea to do. If you were to make this kind of go over here, then make it pick up, go around the inductor, because then all the inductor noise is going to couple onto the ground plane here, right, and add noise to the feedback, right? So that's one of the things that the data sheet was talking about, but this will be connected automatically, kind of, in a sense. And what you can do is kind of just like put another trace like this, just so the inductor or the capacitor isn't affecting the feedback or the ground path of the feedback resistor. And then that just makes sure that it gets connected. And then what you can do too is that you can add, like, for example, if this is a ground plane, you can add ground signal for any like type of signals that you have, right? But this is also just a stagnant DC too, so these are kind of useless. But yeah, this would be relatively fine. And then what you can do too, like I said before, that you can like kind of it kind of worries me that the plus here of the capacitors on this side, I would just be careful of that. Because this is the positive voltage side. But for some reason, this looks like it's the opposite. Yeah. And that's something that you also catch when you do PCB layout. Right? Let me choose a stronger color. That's why. So that's reversed. Yeah, see? That's reversed. Okay, and that's the other things that you run into as well when you do PCB design, is that sometimes it's hard to catch things. And only when you do the layout is it really transparent that the plus is probably a positive voltage, not the ground, right? But yeah, that's kind of the whole idea behind routing, right? It's kind of, you Bob Ross it, and you kind of look at the data sheets, like what signals are you looking at? What, like, where are the wider planes at? Like, you can see very obvious that switch, right? Like here there's a statement about FB, so you want to take any statements you're able to get, and then that helped us kind of like figure out this part right here, right? But you can kind of also tell too what they're doing with the like size of the switch here, the size of the inductor. You might see in other data sheets too that you'll see a lot more of this like taper work that goes into this, right? But this will work. Don't worry too much about the, I'm like 90% confident that this would work, even if you just connected everything through a normal trace like this, right? It's only when you're actually trying to like get the maximum current and the maximum performance out of this when it actually matters to have a good, decent layout, right? And you can, I can definitely make this better, but you have a lot more work to do. So honestly, if this, I would just pass it off as like being good enough, right? Because you don't want to make perfection the enemy of good, right? And that's kind of it. Okay, awesome. I'm going to be stopping the recording.